Hello. Now we're going to look at simultaneous equations and particularly the graphs of simultaneous equations. So what we've got here is a graph of three lines, L1, L2 and L3. To do simultaneous equations, the algebraic way anyway, we need to know what their equations are. So we're going to start off by taking our picture and we're going to find the equations, our x and y and number equations, in order to know what L1, L2 and L3 are. Now, we know that a straight line has the form y is equal to the slope times x plus the y-intercept. Y is equal to mx plus c. So m, again, is the slope, and that's the rise over the run, and c is the y-intercept. Where does it cross the y-axis? There are other ways of getting the equation of a line, but this is the one that we're going to look at today. So, visually, what is L1 going to be? Well, we know it's in the form y equals mx plus c. So y is going to be equal to the slope times x plus the y-intercept. Well, the y-intercept is very easy. It's going to be 2. Y-intercept, where the red line crosses the y-axis, is at plus 2. So we know c is going to be plus 2. But what's the slope? Well, it's going to be the rise over the run. Well, if I run across by 2, I rise by 1. Or put another way, if I rise by 1, I run across by 2. If I rise by 1, I run across by 2. If I rise by 1, I run across by 2. So it's the same slope each time. So that means that my rise over run is going to be 1 all over 2. Every time I rise by 1, I run across by 2. That gets me back to my line. So that's y is equal to a half x, because rise over run ends up being 1 over 2 is a half, plus our y-intercept is 2. Now, when we do simultaneous equations, we tend to want to have no fractions involved. We want to get rid of fractions if we can, and we want to have the x and the y on the left-hand side and the numbers on the right. This is not technically necessary, but it is, in general, the best way to do things, at the moment anyway. So when we do our rearranging of this equation, which we will do, we want to get rid of this fraction, so we are going to multiply both sides by 2, because we do not want fractions. Anytime that we can get rid of fractions, that's definitely what we're going to do. So we end up with 2y is equal to 2 by half is 1, so we end up with 1x. 2 by 2 is 4, so the number outside gets multiplied by each thing inside. And when we rearrange that, we subtract x from both sides, and we end up with minus x plus 2y plus 2y is equal to 4. Now that's in the form that we like for a simultaneous equation. We have x and y by themselves, number on the other side, and we don't have any fractions involved. So this is good. Next, we want to know what L2 is. So we look at the slope here, and if we run across by 1, we pick points where our line neatly crosses the grid underneath, so the grid for our coordinate system. So if we start here and run across by 1, we drop down by 3. So if we run across by 1, we rise minus 3. We have dropped 3 places, so we have risen minus 3. So then my equation is y is equal to minus 3. I've gone down by 3 times x. So minus 3 over 1 if we want. So rise over run. I drop by 3 every time I run across by 1. So minus 3 over 1. Plus, where's my y-intercept? It's 9. So now I want to rearrange this. If I add 3x to both sides, I end up with 3x plus y is equal to 9. So those are my first two equations. Now, what happens with L3? Well, this one is a little bit funny. It's a horizontal line. So its slope is just 0 because there's no rise. I can run across as much as I like, but there's no rise up or down. So its slope is just 0. So that means that the equation of this line is just going to be visible from its y-intercept. Put another way, what would describe all of the points on my green line? Well, what's true of all the points on that line is that y is equal to 9. That's true everywhere. So that's our three equations. These are two equations that we're used to for simultaneous equations. This one seems a little bit funny, but we're going to see what we're going to do with it. Now, with simultaneous equations, algebraically speaking, we know that we would try and add the two equations together in order to get them to, in order to get rid of one of our letters, and that would allow us to solve our equation. Visually speaking, what do we do when we do that? If we got the intersection or the simultaneous equations with L1 and L2, we would end up with an x and a y value. And what does that physically mean? That means that it's an x and a y value that solve both of these equations. Well, that means it's a point that's on both of these lines, the red line and the blue line. Well, what point can we see that is on both the red line and the blue line that has the same x and y for both of them? Well, it's this point here. The point 2, 3 is on both lines. So we say it is the intersection of those lines. So when we are doing simultaneous equations, we are finding where our lines cross over each other, where they intersect. So L1 intersection L2 is going to be at 2, 3. And this is the core of our argument. And now today we have where we're doing simultaneous equations, where we solve these two equations together, what we are finding visually is an x and a y that solves both equations. That means a point that is on both lines, and that's going to be where they cross each other. 2, 3 solves both of these equations. And when we do simultaneous equations with L1 and L2, we should find that the x and y we get is x is 2, y is 3. Can we do the same thing with L1 and L3? Well, L1 crosses our green line of L3 at in the door 14, up the stairs 9. So when we do simultaneous equations there, we should get 14 for x and 9 for y. And where does L2 and L3 cross each other? Where do they intersect? That's going to be at 0, 9. So we have 14, 9, and 0. 9 is our point of intersection there. Now let's put this into practice. We're going to start off with the easier ones, the unusual one, and then we're going to do a more normal simultaneous equation to finish off. So we're going to do L1 intersection L3. So we have L1 and L3 is what we're going to start off with for doing the algebraic method of this. This was our visual work. Now we're going to have a look at the algebra version. So for that, we need to know L1. Well, L1 is minus x plus 2y is equal to 4, and L3 is going to be y is equal to 9. Now, in this particular case, we know exactly what y is. So this is like we've actually done half of the question already. All we have to do is say, well, y is 9. So let's sub in y is 9. So we have x plus 2 on 9 is equal to 4 minus x plus 18 is equal to 4 minus 18 from both sides to get x by itself. Minus x is equal to minus 14. Divide both sides by the coefficient of x, which in this case is minus 1. And we end up with x is equal to 14. So we find that their intersection is at y is 9, x is 14. Exactly what we found visually. Let's do L2 intersection L3, because again, that's the other quick one to do. We write down our equations. So L2 is 3x plus y is equal to 9. That's L2. And L3 is just y is equal to 9. And again, this time we have one of our equations is just y equals 9. So we know y equals 9. Let's solve this. So we sub in and we have 3x plus 9 is equal to 9. Subtract 9 from both sides to get the x stuff by itself. We have 3x is equal to 0. At this point we can say, well, x has to be 0, but we could also divide by the coefficient if we wish to. And 0 divided by 3 is still 0. So we find that the intersection is at 0, 9. Exactly what we found visually. Now let's do our more traditional simultaneous equation, and one for our more complicated lines are L1 and L2. So L1 intersection L2, we use our set notation again to say where they intersect, where they cross each other. So L1 is at minus x plus 2y is equal to 4, and L2 is at 3x plus y is equal to 9. Now, we know that we want to get at the same number with a different sign in front of one of our letters, and the easiest that I can see at the moment is that I can multiply L2 by minus 2. I could also multiply L1 by 3. Either will work. But I'm going to do L1, I'm going to leave the same. And just for consistency, I'm going to call that equation 1, and I'm going to call that equation 2. So I'm actually going to write this as a 1 and a 2. So I've left equation 1 alone, and equation 2 I'm going to go minus 2 times equation 2. So minus 6. Multiply all of this by minus 2, so minus 6x minus 2y is equal to minus 18. Now when I add these two equations together, my plus 2y and minus 2y sum to 0, and I'll be left with stuff only involving x. So I have minus 7x plus 0y is equal to minus 14, and I divide both sides by minus 7, divide by the coefficient of x on both sides to keep my balance, and x must be equal to 2. I'm not quite done here because I need to find my value for y. So I go back to either of my equations, and I think I'll take equation 2. So I have 3x plus y is equal to 9, and I now know that x is equal to 2. So 3 by 2 plus y is equal to 9. So 6 plus y is equal to 9. Get y by itself, and y is equal to 3. So the intersection of L1 and L2 should happen at x is 2, y is 3, which is exactly what we found using our visual method, where our two lines crossed over each other. So that is what we need to understand for our simultaneous equations, that when we are doing this work with our simultaneous equations, where we find our value for x and y, we are finding an x and y that solve both of these equations, and what that means visually is that it's a point that would be on both of these lines, that solves both of the equations that describe the red and blue line. And that is what we need for now.